Yeah, we can go ahead and get started. Thank you guys for coming down. I hope that you're doing well and having a good weekend. It's been a little crazy for me, but I'm getting by. I will be here for a couple hours doing this review, and then I'm gonna take a little break to get together with a friend for a couple hours. But I'll be back later on tonight, like at about 8 o'clock, and I'll hang around all evening tonight. If anybody just needs a place to study, you're certainly welcome around here. And yeah, same thing tomorrow night. I'll be around in the evening as well tomorrow. Then we have class on Tuesday. We're in pretty good shape. There's a little bit of stuff from section 6.1 that I need to go over with you, especially if you haven't watched those little sort of optional videos that I sent out to you. If you haven't, it's okay. Probably when we get to some of those questions today, I'll try to spend a little extra time making sure that everybody's on the same page about that stuff. But yeah, so our exam is coming up on Thursday this week. This whole week is really just about getting ready for that. Tuesday will be a little bit of that new material from 6.1, and then mostly studying, just reviewing for the test a little bit, which is what we're going to do right now. So again, just to remind you, our midterm is covering all of chapter 4 except for 4.7. Which is going to be at least half the exam just based on just that one chapter alone. And then chapter 5, which we're done with now, it's pretty short, but another 30% or so, and maybe on that section. And then just a couple questions maybe from 6.1, something like 10 or 15%. Obviously, I have not written the exam, and I probably won't write it until Wednesday night. That's usually the way I do things. So this is kind of what you need to be working on. And if you need to organize it for yourself, the resources folder is a great way to do that, because I've got the packet in there that's got a whole list of exactly what are the things that you should be able to do. And then not only that, but all those sample exams and practice problems are in there too, along with solutions to all of that. So what I usually do when I do review sessions is just throw practice problems at you. I don't like to just kind of go through all the material again. We'll do that in the course of talking about these problems, and I'm really not in a hurry with this, so we can take it nice and slow. I hope you guys will interrupt me with questions. Don't be afraid to ask a question. First of all, I don't usually jump down people's throat for questions. And besides that, there's probably going to be other people with the same questions too. So if you have a question, somebody else is probably thinking the same thing and would love to have that asked. So just take your time, just ask questions as we go along here. I've been doing this for a long time, so it's easy for me to kind of forget or to lose track of like where the tricky points are. So if I do that, be sure to slow me down and stop me so that we can go into more detail. Does that sound okay? All right, so I'm just going to go through, as you know, there's 2 sample midterms that are already in Canvas, but I am actually going to take yet another one. I have like dozens of these because I have done this so many times. So I'm going to take a third old exam and just run through this exam, and we'll use it as the basis for talking about stuff. So I think that might be a good way to do this. I will number the problems. I think I'm going to go in order of this. This is a sample exam that is not up on the internet, so these should be totally new and fresh problems for you guys. Okay, so this would be a good problem that I would certainly be ready for if I decide to ask you this, which is I'm going to give you a matrix, and then I'm going to ask you about the row space, the null space, and the column space. So let's write down our matrix A. I'm going to make a matrix here, and it's pretty big. So it's going to have it's going to have 4 rows. The first row is 1, 1, -4, 1, and 8. And then on the second row, we have -2, -1, 8, -3, and -18. And then on the third row, -2, -2, and 0, and -2, and 0. And then the last row is going to be 0, and 3, and 3, and -3, and -12. Okay? And what I want to do on this problem is find bases find bases for the row space of A. All right, and then we'll also do the col space of A. And the null space of A. So don't forget about that handout that I have referred to in Canvas that has that recap. There's a half-page summary. You guys know which handout I'm talking about. I've put it on the screen before. It's got like, here's everything you need to know about the row space, the column space, and the null space of a matrix. And you just have to kind of make sure you know that chart really, really well. So before I jump into solving this, let's just, I will start kind of with some just general information here. What is the size of this matrix A, guys? Can I have you guys help me with some of this? 4 by 5. Okay, great. So that's 4 by 5, 4 rows and 5 columns. And so just in terms of the M and the N values that we usually designate for this, that means M is 4 and N is 5. So far, so good. And let's just remember that the row space, so this is just a quick review. The row space of A, this is a subspace of R, which one will it be? Will it be R4 or R5 for the row space? R5, excellent. We can actually see if we look at it, if we forget the right answer, just look at your matrix and look at how many slots are in any row. That's an easy way to get it right. There's 5 slots in any row, so it's R5. In general, it will be Rn. So in this case, the N is 5. The call space, just to get that one nailed down, that one will be a subspace of which one? Rm. In this case, 4. If we just look at the columns, we see that each column has 4 slots in it. So that would mean that we're looking at vectors inside of R4. And then the null space, which is the third one that they're going to ask us about. Can anybody remind me about that? This one is a subspace of which one? Anybody? That's okay, Chris. Rn, which is R5 again. That is absolutely right, guys. There would be, the null space is where you're actually solving the system, and there are unknowns associated with this system, and there's 5 of them, right? There's 5 unknowns. We could label them as, x1, x2, x3, x4, and x5. So if there's 5 numbers filling out that null space, then it's a subspace of R5. Okay, so anyway, so just make sure you know the M and the N thing and which one is a subspace of what. And another thing to just to remember about taking an exam in this class, guys, is the more information you put down on your paper, the more I can help you with partial credit. So if you see this problem and you end up, let's say, either you make mistakes with the EROs or you just don't even have time to really do the whole process. If you've written some of this stuff down, I can give you credit for knowing that. So it doesn't hurt to just spell out everything that you can, that you remember about the row space, column space, and null space. Okay, so in order to find these bases now for the row space, column space, and null space, what do we need to do?
Get it in row echelon form.
Get it into row echelon form. Beautiful, exactly. We have to take this matrix and we have to do a few EROs on it. So I'm gonna work that out over here. So let's just start with our ERO process. I'm gonna be a little bit less fussy in this exam about all of the ERO notations. So, if you want to kind of just go a little bit fast through this, just try to be careful. It'd be better if you didn't make any mistakes with this. The first row has actually been nicely put together with a pivot in the upper left corner to begin with. And then I'm going to take multiples of the first row and add them to the lower rows in order to get zeros below the first pivot. So I have to add 2 times the first row to the second row. Okay, I'm going to do that right now. So doubling the first row and adding that to the second row, I'll get 0 and then 1 and then 0, and then -1, and then -2. Okay? And at the same time, I'm gonna take double of the first row and add it to the third row. So if I take double of the first row and add it to the third row, I will get 0 and then 0 and then -8. 2 times the first row added to the third row. So we have another 0 and then a 16, if I'm doing this correctly. And I'll leave the bottom row the same for the time being. I don't really need to change anything there. The point being that I now have my pivot in the second row, just like so. Okay? And actually, it's not gonna take us too much more work to get to the final answer. The first 2 rows are already good to go. So let's just recopy the first 2 rows exactly the way they are right now. Okay? Be something like that. And on the third row, I see a -8 and a 16. I'm gonna go ahead and multiply the third row through by -1/8 so that I can get a 1 there. So I'll get a 1, a 0, and a -2. So just divide through by -8, in other words. And then at the same time that I'm doing that, I'm gonna take -3 times the second row and add it to the bottom row. So -3 times the second row added to the bottom row becomes 0, 0, 3, and then 0, and then -6. And I can see that, actually, I can now see that the fourth row is just a multiple of the third row. So I know that what will happen, I'll write one more step down here. So the first row stays the same, the second row stays the same, the third row stays the same, and the fourth row gets zeroed out. And this would be a row echelon form. I want to make a quick comment here though, because I can tell you a common mistake that I see. Okay, I'd like to do that, and I see it many, many times. So what happens is students will sometimes notice that the third and fourth rows are the same, and so they'll cross them both off, which is actually not what you can do. You can cross off the fourth one, because the fourth row is going to get zeroed out. When I draw a line through an entire row, I'm basically saying that we can zero that row out. But the thing that you don't want to do is cross them both off, because if you do that, you are actually losing information here, yeah? So I want to keep the third row just exactly as it was. It's just the fourth row that we're getting rid of. Does that make sense? Okay, so guys, this is our row echelon form. I'm pretty sure we won't have to do too many more EROs today. But if you made a mistake and you had the wrong row echelon form here, I would take that result that you have, and basing your answers off of that, I would give you as much partial credit as possible, which would be almost full credit. Because if you know how to find the row space, column space, and null space, once you have your row echelon form, I can give you credit for that. Okay, so don't give up on the problem just because you're thinking that the matrix is wrong. Okay, just deal with the matrix you have and do the best you can with it. Okay, so let's start working it out. The basis for the row space, can somebody remind me, how do we get the basis for the row space? Do you remember that part? Pablo?
No. The
I'll get
basis
you next time.
for the row space will have three vectors because of the rank.
Okay, and what 3 vectors are they?
The first top three.
The first 3 rows, right? And we can take these 3 rows, literally from this row echelon form matrix. So it literally is just these 3 rows. So 1, 1, -4, 1, and 8, comma, and then 0, 1, 0, -1, -2, and then comma, 0 and 0 and 1, and 0 and -2. And it's just those 3 rows right there. Okay, so it's just literally what you see right there in front of you. Okay, so you just write those down. That's your basis for your row space. You don't need to stop and check that it's Li or anything else, because the theory tells us that that will be a basis. Okay, so we're good to go on that. Okay, I mean, I cut you off, but do you want to maybe try the column space for me? Or how do you get the column space? Do you remember?
I think you take the like the part of the EROs where really, it's just the columns that you get from the last part of the EROs.
Okay, so here's our row echelon form. These are the pivoted columns. So what are my three basis vectors for my column space going to be?
Those original columns.
These first three columns of my original matrix A, right? So you have to, the difference with the row space and the column space is that for the column space, you have to go back to the original matrix A and grab those columns. So let's make it into a set here, guys. Notice that when I'm writing down these bases, I am just listing the vectors with commas between them. There's no variables in here, there's no, unknowns or anything like that. I'm literally just grabbing the columns from the matrix A. So the first three columns would be these three. Okay, so it should be these three, and you don't have to, prove anything about that. You just make that list, right? You'll get full credit for that. Yeah, Chris?
We can only use the vectors from our matrix A and not the row echelon form.
For the column space, yes. For the column space, you must use the vectors from the original matrix A. For the row space, it's actually your choice. You can take the pivoted rows here, or we could have gone back to the three original rows here as well. But for the column space, we must go back. Yeah, good point. So far, so good? All right, let's talk about the null space. Now, for the null space, we have to work a little bit harder, because when you have a null space, remember, you're really solving a system of equations where you've augmented the matrix with zeros on the right-hand side. So you have your unknowns here, yeah, that you sort of line up to your columns. X1 through X5 would be the unknowns. And you actually have to solve this by back substitution. Guys, if I ask you to do something like this, it should be second nature by week number 9 of this class, that you are just simply going to set up free variables for the unpivoted columns. So I would probably let X4 be equal to R and let X5 be equal to T. These would be free variables. So we could write them as free variables like that. And then I have to figure out what X3, X2, and X1 are from the pivoted row echelon form right now. So if I look at the third row here, guys, let me just make a little room to write this down. The third row as an equation just looks like X3, 1 times X3 minus 2 times X5 equals 0. Okay, so stop me if this isn't clear, but I'm basically taking this third row and writing it as an equation again. And then I can solve for X3, which is my leading variable, in terms of my free variables. So X3 would be, if we actually solve it, it's 2 times X5, which then we could think of as 2 times T. Yeah, just 2 times T. All right, and then I'm gonna go to the previous equation, the one right above that, where I see X2 as my leading variable. And what else do we have? We have minus X4 and minus 2X5, and that is equal to 0. If I then solve for X2, in this equation, it's gonna be equal to X4 plus 2 times X5. So that would be X4, which is R, plus 2 times X5, which is T. So we get R plus 2T. And then we actually, finally, we're still not done because we have to solve for X1. And X1 just comes from the first row. And this, I'll put it right here, I think, guys. So it's, well, let me actually put it right here. Just wanna make sure I have enough room to show you the entire equation. X1, right, plus X2 minus 4X3 plus X4 plus 8X5, all of that has to add up to 0. So everybody see how I'm getting that? This is just translating the first row of my matrix into an equation. And the coefficients of the unknowns are sitting in the matrix. So I have to solve this for X1. And it's gonna take just a little bit of work. Give myself some room here to write it nicely. So X1, if we solve for it, I have to throw everything else to the other side. So I'll subtract the X2 to the right side, then I'll add 4X3 to the right side, then I have to subtract X4, and I have to subtract 8X5. I have to do all of that rearranging. And this has to still be translated in terms of the free variables, right? So my answer for X1, this is correct, but it's not written in the form it needs to be, which is using those free variables. So I'm gonna stick in what we have now. For X2, we put in the R plus 2t, that has a minus in front of it. And then we have plus 4 times X3, which was 2t. And then minus X4, which is R, and then minus 8X5, X5 is equal to t. So we get something like that, which we now should probably try to simplify. So I am doing a little bit of algebra here, guys, and just don't be afraid of that, okay? It's part of what you have to do. I have a negative R right here at the beginning. Actually, let me just do all of the R part first. So I have a minus R, but I have another minus R later. So putting those together, it's negative 2R. And then if I look at the T part, I have negative 2T, but then I have plus 8T minus 8T, which cancels. So the only thing here is the minus 2T at the beginning that we would want to write down. So that's X1 minus 2R minus 2T, okay? Can everybody follow that all right? If anybody's still having trouble with Gaussian elimination, please don't feel bad about that. It just means you need to work on it. And even if it means you have to come to my office hours and have me, just throw a problem or two at you to make 100% sure. Nobody should ever get out of Math 250B not able to do this. This is just solving a system of equations. So you should expect that this is going to continue to be something I'm going to be trying to make sure that people can do. So let's try to get our basis now for our null space. Now, I have been particularly careful here to list my variables in the correct order. Notice I have X1 first, and then X2, and then X3, so on. Sometimes people will, in the midst of their chicken scratch, they might not have these all written down in the right order. That's okay, but just make sure that when you start listing your answer over here, that you do make sure that X1 is first, then X2, then X3, and so on. Okay, so let's get our braces going. We're gonna make a set for our basis here. Can somebody give me one of my basis vectors? Are you able to just kind of pick it off from the entries that we've got there? Pablo?
Negative 2,
Okay,
1,
uh-huh,
0,
0,
1,
mm-hmm,
0.
nice, how did you get that?
So using the term like they taught us busting out the variable.
Busting out the variables of this expression, right? And in this example, for this vector, I'm busting out the R, right? So if I bust out the R, I'm just looking at what are the coefficients in front of the R? So I have a negative 2, then a 1, then a 0, then a 1, then a 0. And so we just make that into a vector here. Notice it has 5 slots. That's consistent with the null space being a subspace of R5. Okay. Can somebody else give me another basis vector? Let's see. Maybe somebody besides Chris. I've heard from Chris and Pablo. Go ahead, Francis.
So since it'd be with t be negative 2, 2, 0, and 1.
careful, so there's gonna be 5 numbers, -2, 2, 2, okay? 0 and 1, exactly, there you go, okay. And since there are only 2 variables to bust out, then we only have 2 basis vectors. Does that make sense? The dimension of this is, the word we had for this was nullity. The nullity of this matrix would just be 2. Obviously, the rank of the matrix is coming from the dimensions of the row space and column space, and there's 3 basis vectors in each of those. So don't forget our good old rank nullity theorem. The rank plus the nullity should add up to n, which was 5. So in this case, we have 3 and 2 adding up to 5. So that all seems to fit. A quick comment for you here. This is not a huge deal, but you might notice I wrote my row basis vectors as rows. That makes sense that I did that, right? And then I wrote the column space vectors as columns. So I wrote the row spaces as rows. I wrote the column spaces as columns. Actually, to tell you the truth, that's totally optional. I could have written these as columns too, and it wouldn't really be wrong. There is no difference. There is no difference between this vector, for example, and the vector that if I wrote it like this, right? This is just as correct as this is. It's just suggestive of what you're talking about if you draw it as a row, because you're dealing with row space. For column spaces, it makes sense to write the vectors as columns, but that's not a big issue. For the null space, some of you might have noticed that if you check the back of the book on some of those null space problems, they write them as rows again. And that would have been also just fine here too. I wrote them as columns pretty much just because I had organized these x's into a column. But it's completely optional which orientation you give to those vectors. It's actually not a big deal. Okay, any questions so far? I was looking back over my sample exams and I think a lot of them, probably more than half of them, have from this second midterm have a matrix and they ask you to find a basis for the row space, column space, and null space. I got a couple hands up here. Go ahead, Amin.
So just to make sure, the nullity of A comes from the number of free variables?
Yes, it's the dimension of the null space, which is the same as the number of free variables, which is the same as the number of unpivoted columns of the row echelon form. Any one of those ways you want to think about it would be totally okay. Yeah, Ryan.
So with the whole thing at the beginning, you did with the denoting the subspaces.
Yeah.
Column space, row space, null space. Is that necessary to put, because it doesn't look like you really use that info to actually get the bases.
Exactly right. You do not really need this. I like to just remind myself though how many slots I'm going to be having in my vectors. So I can see that my row space vectors, they should each have 5 slots, right? All of these have 5 slots. And then for the column space, 4 slots, right? Which is just common sense because when you look at the matrix, yeah, every row has 5 slots and every column has 4 slots. So there's nothing really very deep about that. All right. Yeah, great point. On at least one of the sample exams, I had a follow-up question where I asked for an orthogonal basis for one of these. I can't remember exactly how I did it. I could have asked that here too. I could ask you to find an orthogonal basis for this row space. And if I did that, if I had done that, you would do all of the work that we already have done up here, right? So for any of these spaces, you would start with just getting any basis that you could. And you would label those vectors, so like v1, v2, and v3. And if I ask you for an orthogonal basis for any of these, what would you be thinking about doing? The Graham-Schmidt process, which we just learned last week, right? So you would go to the front of your exam where it has all of those W's on it. So you have like W1 equals V1, right? So your first orthogonal vector would be just whatever V1 was. And then you'd have to do W2. Remember guys, I'm gonna give you these formulas, so you don't need to memorize these, but W2 would be V2 minus you know, the inner product of V2 with W1 divided by the norm of W1 squared times W1, you'd be able to calculate all of that. Because the vectors, these vectors are just in R5, which means that you have a regular dot product that you can just use to do the calculations. So, you know, if I ask you to take the inner product of V2 with W1, that's literally just the dot product of these two vectors, right? So everybody can hopefully do a dot product of those two vectors, and that number would go right up on top. That would be it, okay? Actually, if I ask you for the orthogonal basis for the row space, most of the work is just to get this first basis in the first place. The rest of it is just gonna be crunching the numbers in this formula to figure out what the W2 vector should be and kind of go from there. And then there's also a W3 vector. In this case, you would need 3 of them. If I only asked you to do the Gram-Schmidt process on the null space, you'd only have 2 vectors. It'd be actually a little bit less work in this example to do the null space. Make a little bit of sense? So I won't go through all of that right here, but that's a natural way to tie the chapter 5 material into this problem, would be to ask you something like that. Okay, I have a sort of a part B to this question. I guess I could call that part A, what we just did. Let's just do a follow-up question here. Still working with the same matrix A. This just says, let S be the set of column vectors of capital A. So in other words, S just consists of the 5 columns of A. And then I'm going to ask you a question. Circle the best description for S. So S is just a set of vectors here. And what are the options? So this is like a multiple choice question. They could be Li, they could be a spanning set for R4, could be both, or it could be neither, right? And I've definitely talked about how I like these kinds of sort of 4-part multiple choice questions. So let's talk this one through as well, okay? So S consists of the 5 columns of A. This column, this one, this one, this one, and this one. Now, if we remember, we can always rule out 2 of the wrong answers pretty much immediately if we just count how many vectors are in S. So to solve this one, guys, let me just remind you, I like to just call this value K. K is the number of vectors in the set S. What would that be equal to on this problem? I just circled how many columns?
5.
5 columns. So this is 5, right? Because S is the set of the column vectors, okay? And then I like to compare that with the dimension of the vector space that they are part of. And in the case of the columns, they are living inside of R4 as a subspace of R4. So the dimension of R4 is equal to what? 4. Excellent. Okay, so what we have here is a case where the K value is more than the dimension of the vector space. So in that case, you do need to remember this, it's almost for sure going to be on the exam, is understanding this relationship. So if I give you more vectors than what the dimension is of the universe that they are in, then what can you cross off right away that can't be the answer?
Linear.
Exactly. These vectors cannot be Li. It's too many vectors. We spent $5,000 at throwing these 5 columns into our checkout bag, and it's only a 4-dimensional universe. So there's no way that you would want to spend $5,000 on that. That's too expensive. It's too many vectors, and obviously if it's not Li, then it's also not both, so we can kind of just cross that one off automatically. The only thing that is still up in the air at this point is spanning set and neither. By the way, guys, be sure to show your work on the, if I ask you one of these, which is very likely, if I ask you one of these, don't just cross off stuff with no explanation, right? First of all, if you happen to cross the wrong thing off, if there's no work there, you will get absolutely 0 points for it, right? If you've got some work there, but then you crossed off the wrong thing, I can at least say, well, they knew what they were supposed to do. They knew that they needed to find the dimension of the vector space and count how many vectors they have, and I want to give you partial credit. So please be sure to show your work. Part of these exams for me is not just how much material you know, but getting it written down onto your paper, right? Showing me that you know this stuff, because I want to give you partial credit, trust me. But I have to have something to base that off of. Okay, so be sure to write this part down, and you might even just say, just put a little arrow there or something. So you're using that reasoning to cross off the Li part. It's just a really good idea. Help yourself out to get credit for everything that you know. Now, in this case, we still have to determine whether we have a spanning set. So those 5 columns, let's remember how we test vectors for whether they are a spanning set. The way we do that, if you remember, is we lay the vectors into the columns of a matrix. So for this spanning set question, we lay our vectors into the columns of a matrix. There's, I guess, K of them in general. And then what do we augment this matrix with? Do you remember how I used to do that?
Number sign.
My little number symbols, exactly. I would put my little number symbols there. If I was testing for linear independence, I would have put zeros in the far right column. But right now, I don't even need to test for linear independence. I already know that that fails. The real question just is whether this is a spanning set. And that means I just need to know whether this would be consistent or not. So based on what you see over here, actually laying the vectors into the columns of the matrix just gives you this matrix. And you end up just augmenting it with the number symbols on the far right. So here's the beautiful thing about it, guys. This was an easy question for me to throw on as a part B, because you've already done the work here, haven't you? These number symbols just get carried along. Remember, they don't really change as you do the process. These are just number symbols now. And my question is, do we have a consistent system or not?
Yes. No.
I have a no, I have a yes, we might have to take a vote. So this is gonna basically be the row echelon form, but if you look at the bottom row is 0, 0, 0, 0, 0, and if that was a pivot, if that was a number symbol, it would be a pivot in the far right column, and that's bad, right? We don't wanna have pivots in the far right, that would be inconsistent. So guys, it's not a spanning set either. And so the correct answer would be neither in this case. So your work from part A already answers that question. We don't have to do anything else. Okay, so if we wanted to give a justification, we could just say there is a pivot on the number symbol in the row echelon form. And so that explains why we did not circle the spanning set part. Again, show your work, guys. Be sure to, there has to be enough there that I don't think you just guessed and got lucky. Okay, because I want to know that you actually know the reason why you're circling what you circle. Okay? Yes, question.
It might be your question, but so
It's okay.
if we get all zeros on the bottom row, then it's for sure that there's a pivot, or is there ever a scenario where it could possibly?
If you get all zeros down here and then you augment with number symbols, then this will definitely be a pivot in the far right column, and it will not be a spanning set. Yeah, good point, good point. Ryan.
Is there a scenario where you can have 3 variables, but it can still be consistent?
Yeah, it could, free variables where it would be consistent, that would be situations where you have a spanning set, but the vectors are not Li. So for that to have happened, let's just imagine that this bottom row didn't even exist. So that your matrix was actually 3 by 5 rather than 4 by 5. So if that was the case, if there was no bottom row here, then you'd have no bottom row here. You basically wouldn't have this row. And if that bottom row wasn't there, then take a look at what you're gonna end up with. Now, you don't have pivots on those number symbols, but you do still have free variables. So, yeah. That would actually make a nice test question. I could ask you, give me 4 examples of vector spaces and sets. One where the correct answer is Li only, one where the correct answer is spanning set only, one that's both, and one that's neither. And just see if you could do that. So I wasn't necessarily gonna solve that right now, but that'd be a fun little practice problem for you guys. See if you could make 4 problems. You become the professor, write the question. See if you could write 4 questions that have all 4 of those as the 4 different answers. That'd be kind of a good little exercise to see if you kind of understand what's going on. Yeah. Anyway, everybody feel okay about this? Okay, so it's a very, very likely topic to ask you about row space, column space, and null space of a matrix, and related things like this. This is another very, very commonly asked question that I might have, is this 4-part multiple choice question here. Okay, if we're okay on that, I might move on to a new topic or a new question. Let me go on to number 2. And for this one, I'm just going to ask you to decide, and this will be yes or no, so I'll just write it as y/n, decide yes or no if S forms a subspace of V. So I just want to give you a few of these. I think I have 4 parts to problem 2 here, 4 parts. So let me jump in with part A right here. So I'll give you a vector space. In this case, I'll start off on part A. I'm going to give you R4. Okay, so we all know what that is. Those are just vectors with 4 slots. And then S is going to be the set of x1, x2, x3, x4. So it's the points x1 through x4 such that x3 is less than or equal to 0. Okay. So in other words, the third entry of the 4 needs to be a negative number, basically, or 0. So this is a yes/no question, but how you're going to write it up will depend on obviously which way it goes. And so it's a good idea to not go just blindly into this. Like, you want to at least have a rubric or a template, and you want to try to get an idea whether you think it's supposed to be yes or supposed to be no. So don't feel bad if you want to just sit there for a minute or so and just think about it. It's okay to just pause and think about it before you just launch into writing it out. Okay, don't try to just, play mind games with the professor. Oh, this must be a no for whatever. Just give yourself permission to just sit there with it for a second. What is something that is usually a good first line of tests that we sometimes use for this? Yeah, the 0 vector check, right? So I still don't know the answer to the question yet, but I'm just gonna check that 0 vector because that's an easy thing to do. Now, in this universe, which is R4, in that universe, I know what my 0 vector is supposed to be. It has to be the vector of all zeros. And I need to stare at that vector and ask myself, is it inside of S? So would it be inside of this condition? I mean, would it be a vector that's in S? The only requirement is the third slot needs to be less than or equal to 0. Is that true?
Yes.
0 is obviously less than or equal to 0, so it does pass the 0 vector check. So if it passes that check, that doesn't mean that the answer is yes. It just means we cannot say no immediately. We can't say no immediately. So let's think a little bit about what else we would have to consider here. For subspaces, right, the main thing is whether they are closed under the two operations, addition and scalar multiplication. Okay, so again, before I write anything down, I just want to get an idea what the answer might be. If I added together two of these four tuples, if I took x1, x2, x3, x4, and I added it to y1, y2, y3, y4, where the third slot of both of them was less than or equal to 0, if I added those together, would the result still be in S again, with the sum of the two vectors? Do you think it would still satisfy this condition? If I take a negative number and I add it to another negative number, what do I get? For sure, another negative number, right? So if the third slot of two different vectors are both negative and I add them together, then it's probably still going to be a negative number. I'm pretty sure that closure under addition passes, right? So closure under addition passes. However, before I write that up, I want to think about, so if I wrote that up, then of course the next thing I would have to do is I would have to check the scalar multiplication. So the scalar multiplication would be if I take one of these vectors and multiply it by any scalar, would the resulting vector still be in S? If the third slot is negative and I multiply it by any scalar whatsoever, would it always result in still having a negative number there?
No.
I don't think so. I don't think so, because if you take a negative number times a negative scalar, it is going to flip the sign of that third slot and make it positive now. And that positive third slot is going to be a deal breaker, right? If the third slot comes out positive, then it's going to be no, it's not in the set. So I don't even need to really think about the addition part. If I can see ahead in my mind that the closure under the scalar multiplication is going to fail, I can jump to that. Because remember, if anything fails, if any of these conditions fails, it's game over immediately and we can just stop. Now, we have to give a justification for this, which means I need to give an example of something that is in S. Does somebody want to give me their favorite four tuple that has a third one that's less than or equal to 0? Homan. -1, sorry, louder.
-1. And this -1.
Okay, there we go. That is in S for sure. Okay, excellent. And then I need to take a scalar value. Can somebody give me a scalar to work with here that would be helpful?
-1.
How about -1? Okay. And if I now do this scalar multiplication, so if I take -1 and I scalar multiply it onto my vector -1, -1, -1, -1, I'm going to get 1, 1, 1, 1. And that does not have a negative third slot anymore. So this is not in S. So this is where we put the slash through our element symbol. This is not in S. Guys, this part here is absolutely required. If you're not telling me whether things are in or out of S, then that's kind of missing the point. I have to know that I started with something that is in S, and then when I did the scalar multiplication, it fell outside of S. Now, guys, this is a scenario where if you lose one time, you lose the whole thing. It fails that property. So you could have 25 examples that do work, where you have a vector in S and you picked a scalar and then you did the scalar multiplication and it was still in S. That's fine. But if there's even one time where you can make even one example that shows that it doesn't work, then your property fails. And you can just write that down as your example and be done with it. Okay, so that's why when these properties fail, every time we have one of these, you're always seeing me get out some specific numbers, right? I always like to make specific vectors out of this because that way I can just immediately say, no, this is not in the set and therefore that property fails. When you have a scenario where the properties do work, then I'm not gonna be doing specific numbers, I'm gonna be trying to write it out using the letters and doing the general verification. It's really quite a difference, right? You can really see it on somebody's paper. Are they verifying that the property passes? In that case, it's all just generic letters that I'm seeing on their paper. Or are they trying to show me that the property fails? In that case, I'm expecting to see a whole lot of specific numbers that are being used because I just need one specific example to show that it fails. Make some sense? Yeah, so that one fails the scalar multiplication, and so this one is a no. We don't even have to say anything else about it. Okay, let me give you another one. Am I going too fast though? If there's any questions, just slow me down. I get excited. It's probably not that you're not getting it, it's just I get excited, so I go a little fast sometimes. Okay, let's try another one. This is part B. Let's do this. This is a little bit more writing to write this one out. B is going to be P6 of R. So I'm gonna go to the universe of polynomials. This is polynomials of degree 6 or less. And then S is gonna be, give yourself enough room here, guys. This is gonna be a fair bit of writing. The first term is A minus 3C, all multiplied by x to the 6th. And then the next term is plus 2A plus B minus 3C times x to the 5th. And then the next term is plus negative A minus B plus 4C times x cubed. Okay, and then plus the next term is 5A minus 4B times x, and then plus 7B. All right, and I'm going to put such that A, B, and C are real numbers. So this is yes or no. Yes or no, is S a subspace of V? So I can see that I'm living in the big universe of P6 of R. And I'm only looking at polynomials that have this form right here. Okay? Polynomials that have that form right there. So let's start off with our zero vector check here, guys. Now keep in mind, I forget how many points this problem was worth. I guess it's just 5 points. You know, you're not gonna live and die by the zero vector check. So what I'm trying to say is that's not gonna be a big, you know, you're not gonna accrue a whole bunch of points by just checking the zero vector on everything and then forgetting everything else. So make sure that you can do more than just the zero vector check. But it is a good place to start. The zero vector check is where we take the zero vector of V. Now in P6 of R, that zero vector is actually just the polynomial that has all of these coefficients of 0. So 0x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0x squared plus 0x plus 0. It's literally that. That is your zero vector. Okay. Notice I'm not trying to write down any slots here. We don't have slots when we're talking about polynomials. So try to avoid getting this mixed up with the notation of, say, R6. But we do have these different powers of x like this. Now the question is that in the form of the set of S here? Well, remember, A, B, and C can be any numbers. And specifically, they can be 0. If the A, the B, and the C, if they were all 0, then what would you actually have created? You would have created 0x to the 6th, 0x to the 5th, 0x cubed. You might be like, well, where's the x to the 4th term? Well, that doesn't really bother me. I mean, I have a 0x to the 4th here. I can add that there if I want to. Right, it's no big deal. But I can continue down the line, 0x cubed, 0x squared. This term, if A and B are both 0, then you have 0x and plus 0, right? So this is in S. I would say this is in S. You just put your check mark there. You can just say that. I would consider it to be kind of obvious. Just to give you a reason in case you want to review this, you can just say by putting A equal B equal C equals 0. Like if you put all those values of 0, then this is what you would end up with. Yeah. Okay, so it does pass the 0 vector check. So then we come to closure under addition and closure under scalar multiplication. And the question would be, well, if I took 2 of these, which would mean I take this one and then I have to take another one with different letters, maybe instead of A, B, and C, my second polynomial, I might use D, E, and F, right? And then I would add those together and ask myself, is it still in the same form? The form being this whole thing. You can see that's pretty messy. I don't see people doing that probably on just one line. You'd have to like take this one, add it to another one, then you'd have to like clean up the coefficients, all that good stuff. So I'm seeing it as being a real pain to actually write out closure under addition. So is that really what Dr. Ann's asking me to do here? So, I mean, the question would be, is there any other way besides going through that? I know that's the way I pitched it on that first example. I checked closure under addition and scalar multiplication. Is there another way that we could convince ourselves that this is a subspace? Holman?
I think the span.
By expressing it as a span. That's what you mean, right? Remember, guys, that I'll say it again, I'm a broken record, and you've heard me say it 50 times, which means it must be important. Anytime you take the span of anything, you always have a subspace. So if I could re-express this as a span of whatever, then I would know that it is a subspace, and I could just say that, right? So it was not given to you as a span, but I might be able to represent it that way. I would like to note here, guys, that if I think about S, one thing I can do is I can take my expression, and what can I do with it? That's it. That's it. I can bust out the variables. And by variables, I mean A, B, and C. I do not mean X. X is actually part of the polynomial. So I am going to bust out the A, the B, and the C. So when I bust out the A here, notice I have X to the 6th, right? And here I have a 2 in front of the X to the 5th. And then here I have a minus X cubed. And then here I have a 5 times X. And then there is no A on the constant term. So it would be all of that plus, it's like I'm gonna need more room anyway. B, so I'm gonna bust out the B right now. I don't have any B on the X to the 6th term, but there's one right here in front of X to the 5th. And then here's a B that has a negative in front of the X cubed. And then here's a B that has a negative 4X. And then that last term has a plus 7 on the end of it. Okay, so I'm definitely not seeing this exam being possible without busting out the variables somewhere. We've done a lot of that. The third variable would be the C. And on that one, I have negative 3x to the 6th. And then minus 3x to the 5th. And plus 4x cubed. I guess that's the whole thing. Those are the places where I see a C up there. And so what I'm looking at here, guys, I put this into my big braces again. What I'm looking at is linear combinations of this guy, and this guy. In other words, when you take all possible linear combinations of those three specific polynomials, you're forming the span of those polynomials, right? So this just becomes the span of these three polynomials. I guess I'll write them down one more time. X to the sixth plus 2x to the fifth minus x cubed plus 5x, comma. And then my second vector, x to the fifth minus x cubed minus 4x plus 7, comma. And then the last one would be negative 3x to the sixth minus 3x to the fifth plus 4x cubed. Something like that. And so I will circle yes for the answer here. And that is just since a span is always a subspace. So anytime you take the span of anything, you always get a subspace. Everybody follow that? Now, just to be clear, if you wanted to check closure under addition and scalar multiplication, that would be fine. You could do that. It's just it would be a lot more writing. It would be a lot more work because these are messy looking vectors. So it's easier here to just express your set as a span. That's always an option. Ryan.
Are there any other like kind of cheats like that with this, like taking the span that would make it automatically true?
If your subspace was a null space of a matrix, or a row space or a column space, right? If you had something that was any of those would always be automatically subspaces for sure. Aside from that, not so much, yeah. By the way, guys, here's why you need to make sure you get a good night's sleep before the midterm. All I have to do to completely change this answer is stick a little +1 right there. If I did that, if I just put a little constant in there, then this is not the correct busted out version because there's one extra term there, which is plus x to the fifth. Right, this would be a 1 times x to the fifth here, and it doesn't have any letter A, B, or C with it. And in this case, if you had that, then if you choose A, B, and C all to be 0, you would have gotten a 1 here. Right, and so that would mean that this vector, sorry, I shouldn't change what my 0 vector is. This is the 0 vector, but if I add that +1 there, then this would be not an S anymore. By just that one little sneaky constant that gets thrown in there. So you do have to watch this really carefully. Something like that, you'll catch it hopefully with just the 0 vector check. But just be careful. It's very, very small difference between something that is a subspace and something that's not. Okay, so far are we doing okay? I've got a couple more parts here, guys. Oh, actually, there was a little bit more to these instructions on this problem. It says decide if S forms a subspace of B, and then if yes, find a basis for S. So if yes, let's follow up with that. If it is a subspace of B, let's find a basis for it. That's a natural follow-up question. So let's do it for this example here. A basis is probably, to be honest with you, it's probably the most important concept in vector spaces. So you know that this is something that you're probably going to see on Thursday. We've definitely talked a lot about it. So we need to try to know how to find bases for things. Whenever your Subspace is expressed as a span. What I want to point out, I made this point very recently. Whenever your subspace is a span, then the vectors that are creating that span are automatically a spanning set for it. So these three vectors are already a spanning set for S, because S was created as the span of those vectors. Really, the only question is going to be, are they Li? Are these vectors linearly independent or not? So let's check Li for the three spanning set vectors above. So my follow-up question is, if it's yes, we're supposed to find a basis. These guys, even before I take a breath, these three polynomials are halfway to being a basis. They are a spanning set. But I just want to remind everybody, a basis has to be two things. It has to be a spanning set and it has to be Li. So right now we've got a spanning set and I just want to check Li. How do I check linear independence of a set of vectors?
When you put the vectors into the columns.
We lay them out in the columns of a matrix and we augment it with zeros. Exactly. So we are going to take these polynomials and lay them out vertically. So this first polynomial, x to the sixth plus 2x to the fifth and so on. That, now remember, when you're laying the polynomial here, you're only putting the coefficients of that polynomial into the columns. You're not actually literally writing the polynomial down. So I have a 1x to the sixth, a 2x to the fifth. I do not have any x to the fourth. I'll put 0 for that. The x cubed coefficient is -1. There is no x squared coefficient. There is a 5 on the x coefficient, and then there's no constant term. So my first polynomial has to be laid out as an entire column of numbers like that. Okay, and then I'm going to do the same thing for the second one. X to the fifth, that has a 1 in front of it. There's no x to the fourth. Oh, I'm sorry, you know what? I'm screwing this up, aren't I? Because I should start with x to the sixth. Sorry, the highest power is x to the sixth. So on the second polynomial, I actually don't have any x to the sixth, so there should be a 0 there. Then I have an x to the fifth, a 0 for the x to the fourth, -1 on the x cubed, no x squared, -4 on the x coefficient, and then a 7 for the constant term. And then the last one, I have -3 times x to the sixth, -3 times x to the fifth. There's no x to the fourth. There is 4x cubed, and then there's nothing else after that. So all of the rest of those coefficients would be zeros. And then we have to augment this matrix with all zeros. So this would be the setup for testing for linear independence. Okay, so I'm actually going to just very quickly do the EROs here. We won't spend too long on this because it's kind of old stuff. But we have a tall, skinny matrix, so we've got a pivot right away in that first column. And I'm going to take multiples of the first row and add them to the lower rows to get that whole first column zeroed out. So my goal right now is going to be to get that whole first column zeroed out below that pivot. That's going to be the idea. So on the second row, I have to use -2 times the first row and add it to the second row. -2 times -3 is 6, and I add that to -3, I get 3. Obviously, by the way, the far right column, we know what that's just gonna stay zeros forever. And just fill that all out right now. The third row is completely all zeros already. I won't worry about that. The fourth row, if I add the first row to the fourth row, I'll get a 0, and then -1, and then 1. And then 0 and 0. And you know what I can do? So here's I've already got a pivot right there. I'm not even gonna finish this. I'm just gonna put question marks on this because I can tell that when I add the second row to the fourth row, I'll end up getting a pivot here as well. When I go to the next step. I'm just trying to save some time here, guys. This is a huge matrix. So I can actually get pivots in all three columns. What does that tell you if that happens? Li, exactly. Yes, these are Li. Basically, this means that all of the constants would have had to be 0. So they are Li. And so they're already a spanning set, and now they are Li, so that makes them a basis. Okay, so my basis in this case would be just this list of polynomials. I'll write them out. X to the 6th plus 2x to the 5th minus x cubed plus 5x, comma. And then the second one would be x to the 5th minus x cubed minus 4x and plus 7. And then the last one is negative 3x to the 6th minus 3x to the 5th plus 4x cubed. So there's your basis. And so what is the dimension of F's? The number of vectors that I just wrote down is 3, right? So this is 3-dimensional. My original vector space has a dimension of 7. So this is a 3-dimensional subspace of a 7-dimensional universe. That's the overall big picture of it. Good enough? Questions on that? Okay, let's go on to the next problem. We're just going over, this is, if you came in late, we are simply doing another practice exam. Actually, this is the one I gave last semester. So I'm just going over the exam I did 6 months ago. So let's just try problem 3. I'm gonna skip over a few things to kind of jump around a little bit, unless there's a question here. So far, so good. I guess I can just use this space right here. Okay, Diego.
Wait, so because there was a pivot in the 3 columns?
Yes.
You were able to determine that it was Li?
Right, because if you solved this by back substitution, right, you would be forced to make every single one of your constants equal to 0. There would be no free variables, right? If there's no free variables, then that means the only way to solve your system, which is basically building linear combinations of these 3 polynomials, the only way to do that is by cheating and putting zeros in front of all of those coefficients. Yeah, so yeah, this just means Li when you get pivots in all of the columns like that. Great, any other questions so far? Okay, would you guys mind if I throw a linear transformations problem at you, even though we barely started chapter 6? Can I see if I can test you with it? Let's see how we're doing with it. This will be good. This means if we do it, then by Tuesday, you guys are gonna already know what's going on. So let's try it. Let's let T. Remember, I use T for my linear transformation. And this is the thing where we have inputs and outputs coming from 2 different vector spaces. So we just talked about this at the end of class last week. So let's take R2 as the input vector space. And for the output vector space, I'm going to take P2 of R. And I'm going to let this be defined. So I'm creating for you guys a function, right? I'm making a function from one vector space to another. I'm going to plug in 2 values, A and B, because R2 would have 2 inputs. So I'll write it as A comma B. And then I'm going to make an output that has to live here in the universe of quadratic polynomials. So what am I going to write down? Well, I'll have maybe this constant term, 2A minus B. And then an x term, which might be 5bx. And then an x squared term, which might be a plus 4b times x squared. Okay, and the problem is going to ask us, is T linear? So I'll go slow through this one because I know we haven't talked a huge amount about this. I did do a couple of examples on Thursday, but we're really gonna spend a lot of time on Tuesday talking about this topic. But I'll go a little slow over it today, since it's a little bit new. Remember that when I say is T linear, I really mean, is it a linear transformation? This is just my brief way of asking that question. And does anybody remember what a linear transformation was, or what the conditions were? Holman? Yeah, there's something for addition and there's something for scalar multiplication, just like we have for subspaces. Namely, T has to respect addition and respect scalar multiplication. That's what it is. Okay, so we have to check whether T respects addition. And then if it passes that, then we can check if it respects scalar multiplication. Remember, if it fails at any point, if anything goes wrong at any point, we can stop, right? As soon as something goes wrong, it's definitely not linear. But I'm gonna check that T respects addition. Let me remind you what that formula was. This is just where you take T of, let's say, V1 plus V2. And the question is, does that equal T of V1 plus T of V2? This is the question that we're looking into right now. Okay, so we're gonna check this. I actually need a little bit of room. I think I'll come over here and finish that. So we'll check if it respects the addition, and then if it does, then we'll check if it respects scalar multiplication. So for the addition, I have to take two vectors, you see V1 and V2, I have to take two vectors from V. And I've got my points that look like this, A comma B. So if I take two of those, so let's just check it over here, guys. If I take two of those, I might take A comma B and add that to C comma D. So I would do something kind of like this. And I want to see whether I can split it apart, right? I want to see whether T actually can be busted into two pieces here. Before you can bust it apart, though, you actually have to combine together what's inside the input here. So I have to make one single point out of these two. So A comma B, if I add that to C comma D, I end up getting a single point which has a first slot of A plus C and the second slot is B plus D. Okay. And I think I talked to you guys on Thursday about being very careful on the formatting here. We want to have white space over on the left side. We don't want to keep manipulating both ways. So just make a chain of statements on the right side here going right down your page. Okay, that's going to be the most organized way to do it, I think. So let's see if we can figure out how to evaluate T. They gave us the formula for it. Anytime I want to plug something into T, this is how we do it. We take so for this first constant term, right? So my output is a quadratic polynomial. For the constant term, I take double of the first slot and I subtract the second slot. 2A minus B. So 2 times whatever's here minus whatever's here. Let's write that down for this case. 2 times whatever is in the first slot, right? Minus what's in the second slot. So I'm gonna write all of that down. I'm gonna put some brackets maybe if I need to help myself visualize that. And then plus my X coefficient is just 5 times whatever the second slot was. So in this case, that would be 5 times the quantity B plus D, and that's the X coefficient. Okay, and then finally, we have the X squared coefficient, which is just what? The first slot added to 4 times whatever is in the second slot. So let's come over here and let's take the first slot, which was A plus C, and add that to 4 times the second slot, which was B plus D, and all of that is times X squared. So this is a key step. This is a key step where we're taking the point from R2, we're plugging it into T, and look what we're writing down now. We're writing down actually a quadratic polynomial, which is something on the output of the transformation. It's an output value. Now, the question is, we don't know this yet, so I'm gonna keep us in suspense for a minute. But the question is, can we split this up and just do T of the first one plus T of the second one? We want to know, is that going to be legitimate? We're checking basically this condition right here. Okay. Because sometimes you can get to a place like this and you're like, I don't know what to do next. It's like a big, long, messy thing. It's got a bunch of stuff here and people get a little confused about what to do next. And so I want to remind you that you have a North Star on this problem. You know where you're aiming for, where you're trying to go is you're trying to end up with this. Okay, now this thing has all of the AB stuff in the front and it has all of the CD stuff in the back. And this is the secret to how to think about how you want to break this down. Anything involving A or B, you want to kind of reorganize it into the front. Anything involving C or D, you want to throw it to the back. So right now they're all kind of mingled together. I see A, B, C, and D kind of all over the place, but you can regroup these terms, you see. This is the idea, is to try to regroup these terms. So when I see the 2A, I see a 2A here and I see a minus B here, you can go ahead and grab those and put those in the front. And at the same time, maybe leave a little space and then over here you can put the 2C minus D. Because remember, the AB stuff is going to the front, the CD stuff is going to the back. So I've taken this first term and I've kind of broken it apart into two sections according to which letters you have. Okay, same thing with the X coefficient. I have some terms involving A and B in the front, and then anything involving C or D, I'm gonna put it in the back. So I'll have plus 5BX here, but I'm also gonna have plus 5DX here. So I split the D part to the back. And then finally, on the X squared coefficient, I know it looks a little messy, but all I'm doing is I'm just gonna take the A and B parts, which is an A plus 4B X squared, I'm gonna put it in the front. And then I'm going to take the C plus 4D times X squared and throw that in the back. So this is how it would look all written out. And if I may, I'm just gonna use some really big parentheses here, guys. Some really big parentheses to separate out the A and B parts in the front from the C and D parts in the back. And all of this stuff that's right here listed in the front, that is exactly T of AB. T of AB, that is literally exactly that. And this is the same thing. This is the same thing, but with C's and D's instead of A's and B's. So it actually does pass this test. This is a check. Sorry, this is a check right here. It does respect addition. T does respect addition. Okay, sweet. Any questions on that part? Yeah, I mean.
Can you just apply the zero vector check to the test for linear transformation? And if it fails, then can you conclude that it doesn't respect, if it's, can you?
If it fails, okay, so let me cut you off there. I have not explained a zero vector check yet. Did any of you watch the little optional video? If you did, you already know this, and I'm gonna go over it on Tuesday, that there is a zero vector check for linear transformations too. This is not the same zero vector check for subspaces. So when you have a subspace, then the first thing you can do is check, is the zero vector in S? Okay, but there is a zero vector check. So maybe if you guys don't mind, I'll take just 1 minute and explain that there is a zero vector check, because this is what Amin is talking about. And I was going to say this, if T is linear, then one thing is for sure, and that is that if you transform the zero vector from V, you have to get the zero vector from W. So what he's talking about is if I check T of 0 and I don't get 0, then it doesn't pass the zero vector check, and in that case, it's not linear. So just like with subspaces, if the zero vector check fails, then the whole thing is not a subspace. So yes, you could have done that. Now, in this case, what happens if I do the zero vector check? In our example that we're working on right now, if I literally plug in the zero vector. Now, in the case of R2, my zero vector is going to look like 0, 0. If I plug that in, so everywhere I see an A or a B over here, I'm gonna put in 0 instead. Can you see what will happen? So you'll get 0 plus 0x plus 0x squared, and that is the zero vector of P2 of R, it passes that. And just like with the zero vector check for subspaces, if this one passes, then you have to go on and check whether T respects addition or scalar multiplication. Okay, so I didn't get a chance to talk about this on Thursday last week. I was gonna do it on Tuesday. You guys already have a sneak peek at one of the things I'll be talking about in a couple of days, which is this zero vector check for linear transformations. So if it passes that zero vector check, then we have to go into verifying whether it respects addition, which we just did. The other one then is, let's go back to what I was doing. I need to check that T respects the scalar multiplication. This is going to be the second part of this. I have to show that T respects the scalar multiplication. And for this, we grab that scalar, which I usually call K. So we take K and we scalar multiply it onto A and B. So we take our point AB, and I'm going to try to see whether I can factor it out. So remember, guys, for respecting scalar multiplication, this we did do last Thursday. What you basically are checking is it correct that the K can just be put way out into the front? That's the statement that you're checking. So on the left side, it's inside the transformation, right? It's inside the parentheses. What I'm trying to verify is whether I can pull it out. And to do that, I first have to do the opposite of that, which is I have to throw the K into the vector and turn this into a single input. So I'm gonna take that K and shove it into the two slots of A and B. So I end up getting KA, comma, KB. It's gonna look like that. And now this is what I want to transform. And you have to be ready to use this given equation. This box equation tells you how to transform everything. So if I have KA and KB, it just means everywhere I see an A, I'm now gonna change it to KA. And everywhere I see a B in this formula, I'm gonna write KB. So let's just write it all out and see what happens. So the 2A minus B becomes 2KA minus KB. That's my constant term. And then plus 5 times, I see the B, but B is now KB. Because the input where I had a B before, now it's KB. So I have to change B to KB. And then the last term is A plus 4B. Well, that's going to be KA plus 4KB x squared, something like that. And is there anything we can do with that? Yeah, there's a K in every single term here. So I can literally just pull that all the way out. So I pull the K way to the outside and I get 2A minus B plus 5BX plus the quantity A plus 4B times x squared. So I can get the K totally factored out. And you know that's where this is going anyway. The whole point is to try to get the K out in front. So that's the key step right there. And then what's left in the brackets, guys, is just my T of AB again. And that does check. It does check. So is T linear?
Yes.
It is linear. It respects addition and it respects scalar multiplication. Absolutely true. That's absolutely true. Okay, super. Any questions on that? There's a part B that we're gonna do, but I just wanna make sure we're good on part A. We're gonna definitely practice this some more on Tuesday. since this is relatively new concept here. But we have a linear transformation. So now I have a part B. And on part B for this question, I'm going to let S be the set of T of 1, 0 and T of 0, 1. I'm going to transform 1, 0, and I'm going to transform 0, 1. And then I'm going to ask, circle the best answer. We've already done one of these today. Now we're going to do another one. The choices are S is Li, spans P2 of R, both or neither. Ooh, this is for sure something to make sure you can do. So if I give you a set of vectors, you need to be able to tell whether they are Li, a spanning set for P2 of R, both or neither. By the way, notice that these are outputs. These are outputs of the transformation. You've plugged something in, but you're going to take T of those things. T of 1, 0 lives over here. T of 0, 1 lives over here. They're in the W vector space. So that's why this says spans P2 of R. It would not make sense to say spans R2, right? Because these are not vectors in R2. These are vectors in P2 of R. These are both going to be polynomials. Yeah. So what do you want me to do first on this problem? We could figure out what these points are. Absolutely. So I could try to figure out what is T of 1, 0. And then what is 0, 1. Yeah, we could like imagine we're going to like evaluate these. Well, T of 1, 0. I find people have a harder time with this than I expected they will. It's just plugging numbers in. So you put in 1 where you see A, you put in 0 where you see B. So looking right here, everywhere you see an A, you're now putting the number 1. And everywhere you see a B, you're just putting the number 0. So when A is a 1, I have a 2 right here. There's nothing here because B is 0. And then plus x squared, right? So 1x squared essentially. So is everybody following that? If I want to, this is a formula for T of any point whatsoever. If I plug in 1 for A and B for 0, my output is going to be this guy. This is just a quadratic polynomial living in the outputs. Make sense? Okay. What about T of 0, 1? Somebody want to tell me what is T of 0, 1 going to be?
-1 plus 5x plus 4x squared.
Okay, that was pretty fast. Let's see, -1 right here, if I put in a 1 for B, plus 5x, and then plus 4x squared. Yep, that's exactly what we wrote down. That's exactly what we wrote down. So these 2 points are literally just 2 plus x squared along with -1 plus 5x plus 4x squared. Those are what your polynomials are. Okay, so then the question is, are those vectors going to be Li? Are they going to span P2 of R? Are they going to be both? Or are they going to be neither? And I think I know the answer to this question without doing any more writing. Well, I should write some stuff down. What do you suppose I want to write down to help me sort of parse this out? We don't need to put it into a matrix. It's much easier than that. Even faster. Homan?
You know, it's Li.
Okay, why are they Li?
Because they're not slow.
There's only 2 vectors and they're not scalar multiples of each other. So this is going to be a yes on the Li part. Okay, so not scalar multiples implies they are Li. Great. Okay, what about what else do you want to tell me about to help me answer this question? Could they be a spanning set for P2 of R? Chris?
is less than the dimension of P2R.
It's nothing too crazy, guys. There's two vectors here. What is the dimension of P two of R? It's 3, right? So let's just take a look at that, right? So we look at the K, we look at the dimension. If I give you less vectors than what the dimension is supposed to be, they cannot possibly span the space, right? So they're not going to be a spanning set, which means obviously they're not going to be both. The correct answer is Li only. These are Li only. Now, the fact of the matter is, somebody said something about putting it into a matrix. You can put the first vector into a matrix and then put the second vector into a matrix and then augment it with, well, you could do 0/number symbols if you want, right? To do this whole thing. And now you can do your EROs. What will happen is a pivot will go into the far right column. That's why I've crossed this one off. But you will have two pivots on the left side as well. And so there won't be any free variables, which is Li. So you can do it all from the matrix, but in this case, see, we don't even need to. We don't even need to do that. Okay. Are we doing okay so far? I am going to go a little out of order on this. I'm going through this old exam. I've done sort of the first 3 problems, but there's several more, and I want to make sure that I leave enough time to get to some of the theoretical examples. So why don't we jump to the end of this exam and do a couple theoretical problems, okay? We've been doing quite a bit of computations. So let's jump to the theoretical stuff. I may not stop right at 6. If you guys need to go at 6, it's totally fine. But I have a feeling it's gonna take me longer than that. Question?
What percentage of the exam would have theoretical questions?
Oh, you should probably look over the samples to get an idea behind that. I mean, I don't know, sometimes I even think of some of these questions as being theoretical. I guess it's mostly you're doing a calculation, but it's kind of like a yes, no question. I would say this exam is a little more heavy on the theory than the first one. 20%, 15%, something like that, I guess. It's enough of an important thing that you're not gonna wanna just blow it off. Yeah, we should definitely try to get these right. So I'm gonna jump ahead. I guess this is problem 7 according to this page I'm looking at. So let's try to answer this question, guys. Suppose that A is M by N with the row space of A equal to the null space of A. And what I want to do is I want to show that N is even. This is N has to be even. Okay. What in the world does this have anything to do with? So we're not doing any calculations here really because we don't have the matrix, right? So we can't actually calculate. We don't even know what the M or the N are for this problem. The only thing they've told us is that the row space is equal to the null space. Is there any relevant big idea? This is not some small little thing in the corner. This is like the big elephant in the room type of concept. Is there a big concept that this is related to? Pablo?
The rank nullity theorem.
Exactly. And maybe you don't see exactly how that's going to help us yet, but if you just write it down, I can give you partial credit for that. So you might as well just write that down. If that's the first thing you're thinking about, I would just write it down. Rank nullity theorem. Okay, and then what does that theorem say? Pablo, since you're on a roll, do you remember what the rank nullity theorem says?
So it's the rank and the nullity to get added together.
Uh-huh.
Equals, total dimension or total. I forget last part, I'm not.
Yeah.
What's it equal to?
Number of columns.
The number of columns, which is n, make sure you know it, make sure you know it, it equals n every time. And actually, that's kind of helpful because we're supposed to show something about n. So here's the n in the equation. So it seems like it's pretty relevant here, right? So that's exactly the rank nullity theorem. Now, the question is, how can we use this to show that n is even? The only thing we are given is that the row space and null space are the same. These are two different subspaces of Rn, right? The row space is a subspace of Rn. The null space is another subspace of Rn, but we're assuming that they're equal. If we knew that they were equal, right, does that tell us anything? Since the row space of A is equal to the null space of A, this is the big assumption that we're sort of working with here. Since we are given that the row space is equal to the null space, we know. Yes, Pablo.
For this problem, it's gonna be 2R equals N. Because the rank would be represented as R.
So how are you tying in the rank to anything you see here?
So the null space, the dimension of the null space is the nullity. And
The dimension of the null space is the nullity, and the dimension of the row space is the rank. If two spaces are equal, then their dimensions are certainly equal, right? If two things are equal, then their dimensions are equal. So what we know, guys, is that the rank of A is equal to the nullity of A in this under this assumption. If we assume that, then guys, these two numbers, let's go back to our rank nullity theorem. The two numbers on the left side are the same. So it's 5 plus 5 or 8 plus 8 or whatever. It's just the same number twice. So if you feed that in, so thus, so basically, Pablo, you basically have it. It's exactly the right idea. You have, instead of adding the rank to the nullity, you can just imagine that it's the rank twice that you've added. Okay, so n is equal to 2 times something. So, and that means it's even. It's like a multiple of 2, which is basically what an even number is. Okay, that is a really nice little application of the rank nullity theorem for sure. Okay, so far so good? Yes, question.
Could you apply the definition of an even integer to this? Like since we have 2 times the rank of A equals n, and the definition of an even integer is 2 times k, could you say something like, let k equal the rank of A?
You could do that, that would be totally fine, but there's no need to like insert this third party variable that sort of takes, it just complicates it by introducing a k. You don't really need it because this is already the definition of an even integer. 2 times some number equaling n. So you don't need the k value, but it wouldn't be wrong to do that. If you decided to call this k and then you said, oh, well, n equals 2 times k, I would totally go for that. Yeah, that would be not really a substantive issue there. Okay, so that is that. Is everybody okay on that problem? This is a good one to stew on a little bit, make sure that you understand it. But again, if you don't see the whole solution right at the beginning, that's all right. Just write down what you do know. And you're pretty likely gonna get some, ideas on how to proceed once you just write down that rank nullity theorem. And even if you write that down and then you get stuck, at least you've got partial credit because you've written something down that's actually very relevant. So the moral of the story here, guys, is write down everything you know as you're going along.
On every problem, just everything.
Everything you know that might be relevant to the problem.
Right.
Otherwise, you will run out of time. Trust me. My exams are not usually known for being too short. As you figured out by now, and that's only because I love everything. That's the trouble. Okay, I've got another one here. I'm going kind of backwards on the exam now a little bit. I'm just going out of order to try to cover a bunch of stuff. This is a true false question. And here is what this says. True or false? The Gram-Schmidt process, which by the way, we have not really reviewed this today. I'm hoping you guys are you guys feeling pretty good about the Gram-Schmidt process? Sort of shaky? Okay, well, I've still got more time to do some examples. The Gram-Schmidt process is a procedure used to replace an orthogonal set of vectors. True or false? The Gram-Schmidt process is a procedure used to replace an orthogonal set of vectors with an orthonormal set of vectors. So if you think you know the answer, just hold on for a second. Let's let everybody kind of digest the statement for a minute. And then once we've written it down and given ourselves a minute to ponder this, then maybe we'll see what you guys think. So, and I put this on this exam probably because I just, the actual process itself is very procedure driven. It's just formulas and you just sort of turn off your brain and just go do the calculations. But I want to make sure people know when they're supposed to use this so that when you're taking your engineering classes and they want to deal with orthogonal or orthonormal sets of vectors, you'll know, when this process should be used. So that's, this one's kind of this is an all or nothing thing in this sense. It's kind of true or false, and we just have to give a brief little reason. It looks like most folks have written down the statement. Maybe I'm going to take a little poll, and we'll just see how you guys are feeling about this. Okay, and don't be afraid to vote. We're going to take a vote. Don't be afraid to vote. Don't worry if you're worried if you might be wrong. It's okay. We're just studying. It's just a practice session, right? So, how many people, raise your hand if you think this is a true statement? Okay, not one single hand went in the air. All right, let's try the other way. How many people, raise your hand if you think that this is a false statement? Okay, that is almost everybody. So this one is not fooling anyone, it appears. Everybody knows what they're talking about. What's wrong with this? Why is it false?
It's used twice where it says you're replacing with an orthogonal set.
No, we don't ever do that. Actually, an orthonormal set is already orthogonal. So you would never take an orthonormal set and turn it into an orthogonal one.
It's used to create an orthogonal set using the set of vectors.
From any set. Yes, exactly. Is that what you were going to say? Basically, yeah, you're taking any set of vectors and you're orthogonalizing them. You're not starting with an orthogonal set. This thing where you replace orthogonal vectors with orthonormal vectors is called normalization. And that's where you just divide the vector by its norm to get the unit vectors, right? So this is false. The idea here is that the Gram-Schmidt process, I'll just write down one sentence here because you would need to justify your answer, right? So we would have to write something. So the GS process is used to create exactly what Amin was just saying, to create an orthogonal set from any set of vectors. Okay, so that's the point. So you just take any set of vectors and you can create an orthogonal set from them. That's how it gets used. Excellent. Okay. So that one is easy enough. Let's do another one unless there's any questions on that. I'll throw another one at you. Adrian, yeah.
The replacing the orthogonal set, that's normalization.
Yes, if we replace the orthogonal set with an orthonormal set, that's normalization where you form u sub I, which is, W sub I divided by the norm of W sub I. That's what they're describing here, and that's not the Gram-Schmidt process. The Gram-Schmidt process is the thing, with the formulas for W1, W2, and W3. Excellent. Any other follow-ups on that? Do we feel okay with that? Okay, let's do, just kind of going backwards here. Let's go back to 6A. This is also true or false. This one just says, let V equal P1 of R. And define, I'm going to define the inner product of AX plus B with CX plus D. So I'm going to take two polynomials that are in V. They would have, basically a constant term and a X term. So AX plus B inner product with CX plus D. I'm going to give you a formula, A squared plus B squared plus 10C squared plus 10D squared. So A squared plus B squared plus 10C squared plus 10D squared is our formula. And then the question is that this is a valid and true or false. That this is, so then this inner product thing I just calculated, is that a valid inner product? On B, so this is true or false, basically, is that a valid inner product? So I want to check that out. Okay, let's come over here and think about it. Are you guys getting those axioms of an inner product learned? This homework assignment that I canceled last week is the first time I've ever done that. So the one that we did it in class. So I'm going to find out probably pretty soon whether that was a good idea or not. You didn't actually have to do that assignment because we did it in class, but make sure that you don't overlook it as something to review. This would have been the kind of problem that would have been on that assignment. Is basically it's asking you about the 4 axioms of an inner product space. So axioms of an inner product. Let me just write them down really briefly for you here again, just so we have them back on the board. We can think about the axioms of an inner product. Would be let's see. The first one is the inner product of a vector with itself should always be positive. The only way it could possibly actually be 0 is if you were working with the 0 vector in the first place. This first axiom sort of has 2 parts to it. So just make sure you don't forget both of those parts. And then the second axiom, anybody remember what the second axiom was? The one where you switch the order. So if we have the inner product of x with y, it should equal the inner product of y with x, exactly. All right, and then for the third one, does anybody remember what the third one is about?
The constant.
Okay, so if there's a constant in, say, the first slot, so I take c times x and we do the inner product of that with y, we're supposed to be able to pull the c out. Okay, we're not necessarily going to have to look at all of these, but I just want to review them right now since we're thinking about this. And then the fourth one has to do with what? Yeah, the addition. So if I added, let's say x1 plus x2, if that was 2 vectors, and we want to inner product that with y, well, I need to be able to split that up. So it's going to look like this: the inner product of x1 with y plus the inner product of x2 with y. Okay. My personal feeling is that there's less memorization to do for this exam than for the first one, but this is one thing that if you need some rehearsal on, make some flashcards or whatever, and just practice these a little bit. I'm telling you right now, this is going to be on the test. I haven't even written the test yet. I know this is going to be there. So for sure, you need to know these. And really, this item is asking us, will these 4 axioms all be true? And we might not know the answer to that just by glancing at the formula that was given to us. We really might need to spend the time to kind of go through them one at a time and look at them. Right? There's nothing wrong with doing that. So, we could take this first axiom. Let's just try it with the first axiom. The first axiom is the one where we put the same vector in both places. So we would do something like the inner product of ax plus b with ax plus b. So you just literally put the same thing 2 times. So you don't use the c and a d, you just use the same vector twice, and you just kind of look at the formula and you say, all right, everywhere there was a c or a d, I'm just putting another a and b again. So this is going to be a squared plus b squared plus, now it says 10c squared, but we're going to write that as 10a squared. And then 10d squared is going to be changed to 10b squared. So all we did is change the c and the d that were here in the original formula, and we rewrote them as a and b again. If we clean this up real quick, you can see that it's 11a squared plus 11b squared. And the question I have for you is, will that be greater than or equal to 0? Yeah, you're squaring these numbers. There's a positive scalar in front and you're adding. So there's no chance to ever end up with a negative on that. And the only way it would equal 0, I'm going to do the little part in parentheses. The only way that it would equal 0 is if a and b themselves were 0. So it equals 0 only if ax plus b is equal to the 0 vector, which would be in this universe would be 0x plus 0. Only if the a and the b were both 0 could you get 0 as an answer out of that. So it does pass the first axiom. So the first axiom is looking pretty good. Let's look at axiom 2. Then in that case, is if it passes the first one, then we should just think about the second one. The second one is saying if I put the 2 vectors in the opposite order, will I get the same answer? So it's easy enough to just write down what that would look like. If I put the cx plus d first and then the ax plus b, if I swap the order of them. So let's be careful with this. In this case, so you see I have the a, the b, the c, and the d, but now it's c and then d and then a and then b. So how does that read when we write it down? When I use this formula, the a and the b are from the first slot, so now that becomes c and d, so c squared plus d squared, right? And then the last 2 terms, which involves the c squared and the d squared, have 10s in front of them, but now the last 2 terms have the a and the b on them, right? So would you guys agree that this would be the formula? C squared plus d squared plus 10a squared plus 10b squared. Does that look right? All I did was replace wherever I had the a and the b, I swapped it out for c and d, and where I had c and d, I swapped it out for a and b, because I put them in different positions. Is this the same as what we would have had in the first place? I don't think so. Actually, I really threw people off on this one. This is only from 6 months ago, and I remember there was everybody was like, "Oh, Dr. M." See, the thing is, I keep talking about how it's usually the first axiom that goes wrong, and like most of the ones in the homework and that we did in class and in my video, it was always the first axiom. We get hung up on that, so I decided to do something a little tricky and sneaky here. People didn't like me for it, but I made it this problem. It was actually the second axiom that does not work. This is not the same. This is not the same as if I did the inner product of ax plus b with cx plus d. You can just see it, right, in the way the formula looks. This expression is not the same as this expression. I can pick values of a, b, c, and d very easily where this number will be different from this number. Right, so this one fails, actually. In this example, it's the second axiom that actually fails, and so the answer to this would actually also be false. This is not a valid inner product because it fails axiom 2. We don't have to go on to any of the other axioms at this point, so we're pretty much done. Just so you know, it actually would also fail the third axiom. Because if you had a constant in front of the ax plus b here, that constant would only affect these two values. It would not be factored out of the entire thing the way that the formula requires it to be. So it actually fails the third one as well. And you could choose, if there's more than one axiom that fails, you can pick whichever one you want and just go with that. So yeah, that is a good point to make. Oh, here's a couple more things we definitely need to go over. Okay. How's my time? I'm okay. Well, it's 6 o'clock. If you need to go, you need to go. I'm gonna keep going though. I want to get through a few more of these. As long as I'm gonna take it, after I'm done with this, I'm gonna take a break until 8. So, and then I'll be back tonight. But I am gonna take a break after I finish the review. You know, back when I was a grad student, I would do these review sessions, and I was not the professor, I was just the TA. Back in the day, when I was a grad student at UC Berkeley, and my review sessions got kind of legendary. Because I would come in and I would just go, this is back when I was like 20 years old, I would go for hours of just these problems and nobody would ever leave. And all of the students from the other classes would find out that I was doing these sessions, and it got to a point where I had to like reserve out a whole auditorium, and I had like 100 people there, and we were like 4 or 5 hours in, and I was like, "Are you guys getting tired yet?" And they're like, and I didn't even know what was going to be on the exam, so they were just kind of, we were just kind of guessing that maybe I had some clue because I wasn't the professor, I wasn't writing the test. But we would just go and go and go forever. Well, I gave those days up a few years ago. Decided, you know what, I'm not gonna go for 4 or 5 hours anymore. I'm just gonna go for 2, maybe 2.5. We'll see if I can get that in another half hour here. Okay. So I did 6A, I did 6B. Let's do 6C. I think that they thought that if they left, the very next thing I was gonna show them was gonna be the thing that was gonna be on the test.
Yeah.
And they're like, we can't miss that. That would be like, that's like shooting ourselves in the foot. So nobody would leave. I just finally had to call and say, okay, I don't think any of us is being served by staying here anymore. We're going home. And we all left. Oh, yeah. I remember that. Okay, let's do another problem on linear transformations. So let's suppose, this is also something that's a little bit ahead of what I've covered, but I'm gonna do it right here. Suppose that T is a transformation from P1 of R to M2 of R. So I'm gonna input a polynomial and I'm gonna output a 2x2 matrix. So we're talking about linear transformations, but here's what I'm gonna do. I'm gonna suppose that this is linear. Now, this is already different than any of the other problems I've shown you. All of the other problems that we had, I gave you a formula for the transformation and I asked you to show that it respected addition and scalar multiplication. Like we had to verify that it was linear. No, that's not what this is. This is assume that T is already linear before we even start. Let's just assume that that's true, such that T of, I'm gonna give you a couple of specific values, T of 1 plus X, that would be a polynomial in P1 of R. And let's just say that the matrix that comes out is this 2x2 matrix right here, 3, -1, and then 2 and 4. And let's suppose that T of 2 plus 4X, that's a different polynomial. Let's suppose that that comes out to be 10, -2, 12, and 12. Okay, So I'm giving you all of this information, and then what I'm gonna ask you guys to come up with is, I want you to find t of 10 minus 3x. And this is the beauty of having a linear transformation, is that if I tell you t of just two polynomials, keep in mind, guys, P1 of R is massive. It's a huge universe of all of these polynomials that look like this, right? There's billions of them. But if I just tell you these two values alone, then somehow we can figure out t of something else. It's really amazing. It's really amazing. So I'm gonna show you how to do this. And again, we're gonna look at this in much more detail on Tuesday, because I have not done one of these before, but I'm gonna show you basically the idea behind this right now. So if you're sitting there feeling like, yeah, I don't think I know how I would do this, no worries, because this is one we haven't really gone over. The idea, guys, is that if t is linear, then we know that, what do we know? We know that it respects addition, and it also respects the scalar multiplication. That was our definition of what it means for t to be linear. Well, if t respects addition and scalar multiplication, then it actually respects all linear combinations. So in other words, what I mean is, if I write down, okay, don't write this down yet, guys, because this is not gonna be the ultimate solution to this problem. But if I write down a linear combination like this, I wanna know, what is t of that? Well, t respects the addition and the scalars, so you can totally bust it apart. You can write it as C1 times t of V1, and then add that to C2 times t of V2, and then add that to C3 times t of V3. Right, you can just totally break that apart. T will respect both the plus signs and the scalars. So if I want to know what t of 10 minus 3x is, I can actually write it, so now let's go back to the solution here. T of 10 minus 3x, what I need everybody to understand is that this is a linear combination. This will be 10 times t of 1 minus 3 times t of x. This is the key step. Right? After all, t respects the scalars, you can throw them inside, and then you can make a single subtraction inside the transformation. It's literally the same thing as just taking 10 minus 3x. My point being that if they're asking me to figure out t of 10 minus 3x, all I really have to figure out is t of 1 and t of x. And that's the way we should approach this. Let's try to figure out, what is t of 1? They did not tell us, by the way, they did not tell us what t of 1 is. They told us what t of 1 plus x is, and they told us what t of 2 plus 4x is. But what I'm saying is, let's see if we can figure out what t of 1 is, and let's see if we can figure out what t of x is. Maybe we can figure those things out, I don't know. If we can't, then we can't do the problem. So let's see. Does anybody have a game plan here? This is all we've got to go off. This is what we have to go off of right here. Go ahead, Reed.
Can we turn the first one into t of 1 plus t of x?
Yes, this would be t of 1 plus t of x. And similarly, this one would be t of 2 plus t of 4x. We definitely could do that. And I probably am going to do that in a minute. That is absolutely part of what we need to do. But there's something else that maybe we could do as well that would be helpful here. See, we can take the 1 plus x and the 2 plus 4x and like build other things from that. Like if I asked you what is t of 3 plus 5x, you could just say, oh, well, that's just 1 plus x and then 2 plus 4x. You can look at that and say, yeah, if you added these together, the 1 plus 2 would give you 3, and the x plus the 4x would give you 5x. So if I wanted to know, well, what's t of 3 plus 5x? Well, you would just add those two matrices together. You get 13, -3, 14, and 16. That would be the answer. You see that? You would basically just add these two matrices together, and you'd get t of 3 plus 5x. But of course, that's not really what I wanted. What I said a minute ago is I want to know what is t of 1 and what is t of x. Can we make, the t of 1 and the t of x out of these things also somehow? Can we play around with it a little bit? Again, this is not something we've had much time to practice with. But I'm gonna give you a little hint here. You might have noticed everything in this little thing here is an even number. If you actually think about it, this is just t of 2 times 1 plus 2x. So if I double 1 plus 2x, I get 2 plus 4x, right? So this is the same thing as that. And we do know that that 2 can come right out. Because it's a scalar, t respects the scalar multiplication. So what I'm trying to say, guys, is that I actually think we do know what t of 1 plus 2x is. Because it's half of whatever t of 2 plus 4x was. So all I'm gonna do is cut these numbers in half. 10 divided by 2, -2 divided by 2, 12 divided by 2, and 12 divided by 2. That's t of 1 plus 2x. You're literally just cutting this matrix in half because 1 plus 2x is half of 2 plus 4x. You see? So now you're kind of seeing how we're playing around with this thing. If I tell you that this is what t of 1 plus 2x is, can you combine that or manipulate that with anything else on the board?
T of 1
I
plus
think I
x.
heard you say, what do you want to subtract, County? I heard you say the word subtract.
This one from the original one.
The one on the far left there, let me just recopy it right here. I like that thought. T of 1 plus x is 3, -1, 2, and 4, right? Well, if you just subtract these, t will respect subtraction because after all, t respects addition and scalar multiplication. And if you use a scalar of -1 on an addition, it's just like subtraction. So if I subtract these, look what I'm actually going to end up with. If I take 1 plus 2x and I subtract 1 plus x, I just get x. And therefore, when I subtract the matrices here, 5 minus 3, -1 minus -1, 6 minus 2, and 6 minus 4, this is what I have for t of x. And that was what I wanted to put right there. That is t of x. That is t of x. So just by subtraction, t will respect subtraction. Okay? So I know what t of x is, but I really need to figure out also, the other thing I need to really figure out is what is t of 1. Can I figure out t of 1 based on what I've already got on the board here? Go ahead, read.
T of 1 plus t of x equals the first matrix.
T of 1, right, this first one here is just t of 1 plus t of x. And we just figured out what this guy is. So I can solve for t of 1 now, right? T of 1 is equal to t of, I'm gonna write it out full-hand, longhand here, guys. It's literally t of 1 plus x and then minus x. I'll just put that in the parentheses there. And now using the fact that t respects everything, I can split that up as t of 1 plus x minus t of x. And t of 1 plus x, they gave us that value. 3, -1, 2, and 4. And then t of x was 2, 0, 4, and 2. And now if I just subtract those matrices, I'm going to get 1, and then -1, and then -2, and then 2, something like that. That's T of 1. And so what is T of 10 minus 3x, which is what the original problem was? It's just 10 times T of 1 minus 3 times T of x. Okay, so using the fact that T will respect that whole thing. So that just becomes 10 times, here's the T of 1 right here, guys. It's the matrix we just figured out. It is a matrix, right? And then minus 3 times T of x we found a few minutes ago over there. It's 2, 0, 4, and 2. And now we just have to simplify this into a single matrix again. So slot by slot calculations, we'll do it. 10 minus 3 times 2, that becomes 4. The top right corner is -10 minus nothing. The lower left corner is -20 minus 12, -32. And the lower right corner would be 20 minus 6, which is 14. That's the answer. But what I hope you can see, guys, what I hope you can see is that we could have actually calculated T of anything. The 10 minus 3x, there's nothing special about that. Right, I could give you I could have said find T of A plus BX. It could have just been any A plus BX, and well, all you gotta do is bust out the A and bust out the B. Basically, use the fact that T respects everything. You just write that down, and so this just becomes A times the first matrix, which was 1, -1, -2, and 2, and then plus B times T of x, which was 2, 0, 4, and 2. There you go. And if you want to make a nice clean answer, you just combine it together. A plus 2B, -A, -2A plus 4B, and 2A plus 2B. That would be the general formula. Make sense? I can't possibly emphasize how important this is. If you're a computer graphics designer and you are trying to do some fancy thing, either like maybe you take your screen, you want to like rotate it or flip it around or whatever. If I tell you where 2 of the pixels on your whole screen get moved by some operation you did, you will then be able to tell me where all of the pixels on the entire screen will get moved. Just from those 2 pieces of information, right? I only gave you 2 facts right here. And from those 2 facts, I'm able to derive T of everything. The whole mystery is solved. I love it. Anyway, I'll try to stop lecturing what I'm going to say on Tuesday. But that's what I'm going to tell everybody on Tuesday is basically that this is a powerful idea. This idea of a linear transformation. Okay. What else do I want to actually cover? Did somebody say they're a little shaky on the Graham-Schmidt process? Are we still?
But
How do you guys feel? Do you want me to practice the Graham-Schmidt process? I can show you one of those real quick. That'd be good? Yeah, let's do it. Let's do it. I don't have that many more here. I've just about done everything, but let's just do a little bit more. I'm still working off of this exam. So this is now I'm going back to number 4 on my little exam page. Number 4 says find an orthonormal basis for the span of, and I'm going to make 2 matrices here, 1, 1, 1, 1, and then 4, 3, 2, 1. And if I do that, Does that question make sense as stated? It does not. It does not make sense because why not?
You need the.
I need the formula.
Yeah.
I need the inner product formula, so let's give it to you here. So where I have a formula that we can use. The inner product of my first matrix is going to be A1, A2, A3, A4. And then I'm going to inner product that with B1, B2, B3, B4. And I'm just going to make, I have to give you this formula. So I'm going to give you something. A1, B1 plus 2A2, B2 plus 3A3, B3 plus 4A4, B4. Actually, the first part of the question would probably be to verify that this is a valid inner product. If it's not a valid inner product, then we wouldn't be able to use it to do anything. So the first part might say, check those 4 axioms. But for the time being anyway, I'm just going to assume that the 4 axioms work and that this is valid. You can assume that too, by the way. On the exam, if I don't ask you to show the axiom, if I don't ask you to verify that it's a valid inner product, you could just take it that as a free assumption. So we're just going to use the assumption that this is a legitimate formula for an inner product of these 2x2 matrices. So just totally making this up. Oops, I forgot my little brace here. Okay, so what is the main tool that you need in order to solve this problem?
The formulas. For, oh,
What's it called?
The
Somebody want to help them out?
GSP?
The Graham-Schmidt process. Yes,
GSP.
5.3. We just did it last week. The Graham-Schmidt process because of the question right here. Find an orthonormal basis. That's my tip off. And if you just write down on your paper, if you just write down, Graham-Schmidt process, but you don't really have time to do it, I don't know. Let's hope that everybody has plenty of time. But if you don't have enough time to do the whole problem, but you at least write that down, I can give you points for knowing that. So write it down, guys. Put it on your paper for me. So yeah, what we're gonna do, guys, is let's just set up these 2 matrices as our vectors, V1 and V2. And then remember, I'm even gonna make your life even easier. I'm gonna give you these Graham-Schmidt formulas. You probably remember the first one. The W1 vector is just V1. So that would literally just be 1, 1, 1, 1. And then W2, I would give you this formula. Let me go ahead and write it down for the moment. It's V2 minus, and then we have to take the inner product of V2 with W1 divided by the norm of W1 squared times W1. So it would look like that. And just so I can have enough room, let me come up here. And I'm going to start filling everything in that I know. So the V2 vector, that was 4, 3, 2, 1. Right? And then I'm going to subtract some fraction that I have to fill in a minute times the matrix 1, 1, 1, 1. So I'm going to have the W1 vector in there. And I just have to put the numbers in here. In the numerator, I'm taking the inner product of the 2 vectors, V2 and W1, which is really just these 2 vectors. The only thing I have to caution you about is it's very tempting to just start doing like dot products. But actually, this is the formula you have to use. So be a little careful with that. So what I'm going to get in the numerator, let me just draw a big arrow to this spot. I'm going to take A1 times B1, that would be 1 times 4, plus 2 times 1 times 3, plus 3 times 1 times 2, and plus 4 times 1 times 1. All of that goes into the numerator that I'm creating over here. So this is going to be 4 plus 6 plus 6 plus 4, I think is 20. Okay, so that's the numerator. And then, is that okay? Everybody getting 20 out of that? I'm having to make sure, so I can't just use a regular dot product. I've given you some other formula. You have to live with whatever formula I gave you, right? So we're gonna live with this formula. For the denominator, we have to do the square of the norm of our vector. So just to remind everyone again, the norm of any vector, right, is the square root of the inner product of that vector with itself. So if I kind of square both sides of that, that will get rid of that radical. So I'm just, in this denominator, I'm literally just taking the inner product of W1 with itself. So how's that gonna look? Let's get the arrow to the denominator here and work this one out. It's going to be 1 times 1, by the way, I'm not even thinking about this vector anymore. It's just the first one here. 1 times 1 plus 2 times 1 times 1 plus 3 times 1 times 1, and then plus 4 times 1 times 1. 1 plus 2 plus 3 plus 4, which is 10 in the denominator. Right? Look okay? So then you're really just subtracting 2 times the second matrix. So what is my answer here? 2, 1, 0, negative 1. And so what my final answer is for this would be the vector 1, 1, 1, 1, comma, 2, 1, 0, negative 1.
That's
Yeah, I know. Hold on.
not bad.
No, you're good. You're good. This is what kind of a basis?
Orthogonal.
It's only orthogonal so far. Remember, guys, that this Graham-Schmidt process is only for the orthogonalization of the basis. So this is an orthogonal basis. I think this is what you're gonna say, Reed, right?
Yeah.
This is actually not what the question's asking. The question says find an orthonormal basis. So the last part of what I have to do is I have to normalize these vectors now. So these would be, this is the W1 and the W2. That's what those vectors are. But we're not done because we need to get the U1 and the U2. That's actually what's still missing. Okay, so let's just really quickly review that part. So we actually need to find the norms of these vectors so that we can normalize them. Right, to be able to normalize these vectors, we have to divide by their norms. What is the norm of W1? Because we actually already did the work for that. What is it? The square root of 10. Exactly. The square of the norm was 10. But we didn't have the big radical on it because we were doing the square of the norm. So if we just want the norm, it's just the square root of 10. Exactly. And then let's do the norm of W2 while we're thinking about it, and then we'll write down our final answer. So for the norm of W2, again, I have to take the square root of the inner product of W2 with itself, this guy right here. So I've got my formula here. I'm just gonna dot this thing with itself using this formula. So 2 times 2, right? I'm gonna write out the terms in here. 2 times 2 plus, and then I have a 2 times 1 times 1. And then plus 3 times 0 times 0. And then plus 4 times -1 times -1. Kind of ran out of room here, guys, sorry. So it's all of that. So that's 4 plus 2 plus 0 plus 4. And 4 plus 2 plus 0 plus 4, is that 10 also? That's also the square root of 10, actually. Great, so both of my vectors have a norm of radical 10, and so now I'm ready, I can now write down my final answer for my orthonormal basis. Sorry, I'm kind of going from right to left here. That's not confusing anybody, is it? Only mentioning that because we had somebody apply for a job in our department not that long ago. And we always make them come give a teaching demo, like practice teaching. And the first thing the guy did, he walked in and he started writing way over here. And he walked all the way, did his whole work this way. And everybody, we were all kind of looking at each other like, what's wrong with this guy? He's doing it backwards. But I never did get an answer from him, like why he does that. I think he was left-handed. I think that's what it was. But anyway, we were kind of thinking, maybe this isn't gonna work out so well. But he's actually turned out to be a really good professor, so it's all good. But now I'm adopting his strategy. I'm kind of going from right to left. I just have to take those matrices there and divide them by radical 10. So 1 over radical 10 times 1, 1, 1, 1. And then 1 over radical 10 times 2, 1, 0, negative 1. And this would be the correct final answer. Yeah. If you threw the radical 10s inside the slots of the matrix and wrote them all down in the denominators for each corner of the matrix, that would be fine. You don't have to. I kind of prefer to leave it like this. It's just a little bit cleaner, but you wouldn't have to do that. So that's a review of the Graham-Schmidt process on a problem where I've given you a kind of a funky inner product, like you've never seen this formula before, but you can work with it and solve a problem that way. Let me just see where I'm at on this, all this stuff. I've done almost all of these things. I kind of want to take a break. Would that be reasonable? I mean, I have a couple more that I haven't done. I think what I might do is, they're not that big of a deal. I might just do them in my next review on Wednesday, and then I'll maybe do them at the beginning of Wednesday's review, and then I can just send them out to you. Would that be okay? Because I just kind of want to take a break before my office hours and just get a little rest. And it's been 2.5 hours. You guys probably want a break too. A little bit of a chance to decompress from all this. I think we've covered almost everything pretty well. I'm trying to think, is there anything I didn't really go over that well? At least mentioned everything pretty thoroughly from the start to the end. So if you've been here for 2.5 hours, you've seen a lot of the stuff. Maybe not everything, but you've seen a high percentage of the stuff that would be for this exam. I have one other thing I want to say. A couple people have sent me emails saying they're really worried about the theoretical stuff for the exam. If that's you, if you're like feeling like that's going to be your obstacle to get over, one thing I might recommend is that you look at the true false items in the sections that you're thinking about. So especially in chapter 4, I would say. And I assigned a few of them, but I didn't assign like all of them. So you might just go through those true false. Let's say you're really struggling with theoretical problems about the rank nullity theorem. Okay, well, that's in section 4.9. There's some true false items there that you know are going to be addressing the rank nullity theorem. So you might do that in addition to the ones that are on the sample tests, because there's some theoretical problems in the sample tests as well. So it's not that we don't have any examples to look at. So you should definitely search through there. And if you want to work with me on any of those, just stop by my office hours between now and Thursday, and I'll do my best to help you out. I'm super stoked that you guys were able to come. Was this helpful at all? Just a little bit? Okay, well, maybe we'll do it again sometime. So, all right, I will let you guys go for now and wish you a wonderful rest of your Sunday, and we'll talk again soon. As soon as 8 o'clock, if anybody's still here this evening.